Yesterday we graphed quadratic functions in standard form. Today's lesson is graphing quadratics in vertex or intercept form. Now if you take a look here, you should see the standard form of a quadratic, which we worked with yesterday, and then today we're going to be doing with the two other forms, and you see them below. On the left here we have the vertex form, and on the right is the intercept form. Be sure to jot both of these down. We will be going over them more in depth, but you want to at least make sure you have them copied down. The first key concept is the graph of a vertex form. This is also in your textbook, and it is on page 11, so if you wanted to turn in your textbook to page 11, you'll also find it there. A few things that I added here about this graph of the vertex form is the vertex is at h comma k, and if you look over here on the right, you'll notice you have the parent graph, which is the most general of the quadratics. It's the vertex is 0, 0, and then we do shift them around, and we went over h units and up k. So h comma k is the new vertex. You will see the h and the k in the general form as well. The axis of symmetry, now be aware that it is a line, x equals h. It is a line that if you were to fold the parabola on over top of, then it would be symmetrical about that line. And if the a value, remember, if you look in the general form, a is the coefficient of the quantity that's being squared. If a is greater than 0, which means that it's positive, your parabola will be concave up, which means that it opens upward. And if the a value is less than 0, meaning it's negative, it will be concave down. Then it would look something like this. That would be concave down. Next up is the intercept form. The intercept form does just that what it says. It gives you the x-intercepts, P and Q, for this quadratic. So I have written there the x-intercepts are P and Q, and the axis of symmetry is directly in between the x-intercepts. So to find those, we add the two x-intercepts and divide by 2. Essentially, you're just averaging the intercepts. This is also in your textbook on page 12, so if you wanted to take a look at what it says in the textbook, it's pretty similar. The only thing they have in this key concept for the intercept form is they also concluded the concavity, whether or not it opens up or down, and the concavity is the same in all three forms. So if your a value is positive, it's concave up. If the a value is negative, it's concave down. For this example, number 1, it says graph y equals 1/2 times the quantity x minus 1 squared plus 3. The first thing we need to do is find the vertex. This is indeed vertex form. So if you were to look at the previous page on the difference between the two of them, this is what vertex form would look like. Your a value is here in front as a coefficient, your h value, and your k value. So when we label our vertex, the vertex in this case is 1, that's the h, comma 3. A common mistake is to think that the negative 1 represents the h value, and that is not true, because in the form it's y equals a and then x minus the h value. So the minus sign is actually in the general form, so it's x minus whatever h is. So for example, if you had x plus 3, then in order for it to go from a negative to a positive, we had to have had a negative h value. So in this example that I have off here to the right, the vertex would have an h value of negative 3. So just be aware of that. The axis of symmetry is, if you just look at your h value, it's always x equals whatever the h value is, in this case 1. and then find two additional values. Usually a good one to find are 0, and in this case I know I'm going to have to multiply by a half, so I'm going to try to find something that I can take half of pretty easily. So let's first do 0. So if my x value is 0, going to go ahead and just go through that. 0 minus 1, so I'm up here in the original equation, is negative 1. Negative 1 squared is positive 1. 1 times 1/2 is 1/2, and 1/2 plus 3 is 3 1/2. So 3 1/2 is an ordered, 0 comma 3 1/2. And then again, I've already decided that I want to choose an x value that's going to be pretty nice for me. So I'm going to choose 3. So when I substitute 3 in, 3 minus 1 is 2. 2 squared is 4. 4 times 1/2 is 2. 2 plus 3 is 5. So 3 comma 5. Now I'm going to pause this and go ahead and graph it. If you want to graph some of these points as well, that might be helpful. Now a few things as you look to the right. Number one, it was a little bit harder for me to graph it on with my little stylus here, but I have my vertex here at 1 comma 3, and then I plotted my point 35, and if you take notice over here I also plotted negative 1 comma 5. Now I did that because I knew it was symmetrical, so I knew that if I had a 3, 5 directly across from that, and then I just count my units, it's 2 units away, and here I have my axis of symmetry dotted, and so I was 2 units away from my axis of symmetry, so I went 2 units past it on the other side, and then I labeled another point, I plotted another point, just to make my parabola look a little bit cleaner. Now, you should notice that this is concave up, so concave up. And then a few other things that I want to point out to you is right here we have the value 1/2 for an A value. One thing that you want to know is that the bigger the number is, so for example if you had an A value of 3, that would make the parabola much skinnier than a parent one of x squared. And then the 1/2 flattens it out, it makes it fatter, compresses it towards the x-axis. So the lower the number, less than 1, now it's anywhere between 0 and 1, because remember negative 3 and 3 actually have the exact same shape, one just is concave up and the other one's concave down. So the actual structure of something that had a coefficient, an A value of 3 or negative 3, would look very similar. It would just, one would be up and one would be down. For this example, example number 2, it says, suppose an architect designs a bridge with cables that can be modeled by the function that you see right in front of you. Just to point out a few things, your A value here is 1 divided by 6,500, and you have x minus h, which is 1,400. Positive 1,400 is your h value, and plus 27, which is your k value. That's your vertical placement. 1,400 is what tells you left or right. 27, it moves the parabola up and down. Where x and y are measured in feet, compare this graphs to the graphs function in example 2 in your textbook on page 12. For clarification, I went to page 12 in my textbook, and this is example number 2. So here it says your A value is 1 divided by 7,000, x minus 1,400, quantity squared, plus 27. And the question asks, is it narrower, which it makes it skinnier, or is it wider, compressed to the x-axis? This is what we were just talking about. If the A value, the smaller it gets, the wider the parabola looks. So even though maybe a little bit harder to understand, the 1 divided by 6,500 is actually a bigger number than 1 divided by 7,000. It's kind of counterintuitive. However, as the denominator gets bigger, the number gets smaller. So 1 divided by 7,000 is actually wider, more compressed than what is 1 divided by 6,500. So I suppose rereading the question, is this example that we have written down narrower or wider than example 2? We would say that it is actually narrower, meaning it's steeper or stretched or skinnier, however is easiest for you to understand. The next question after that says, how do the vertices compare? Well, the vertex of the one that is in the notes is 1400, 27, so that's your HK. So 1400, 27 is your HK. And of the example on page 12, it is the exact same. So they are the same. They are the same. And the axis of symmetry, well, if they both have the same x value, then the axis of symmetry are the same. For this example, it says, example number 3, graph y equals negative x plus 1 times the quantity x minus 5. This form is a little bit different. This is because it is the intercept form. So if you look back at your notes or in your textbook to page 12, you will notice that this form does resemble the intercept form. Now, before we find the vertex, it's best to find the x-intercepts. So let's go ahead and just write this general form of intercepts up above. So our p-value is x minus p, but this says x plus p, so that means that this one right here would have a p-value of -1. So one of our x-intercepts is -1, 0. And then from the second factor here, it says x minus q, x minus 5, so our x-intercept is 5, 0. I'm going to go ahead and plot those points on my x-axis, 5 and -1. And then now it's a little bit easier to go ahead and find my vertex because you add your x-intercepts. So -1 plus 5 and divide by 2. That gives you the x value of the vertex. So 4 divided by 2 is 2. Now keep in mind that's the x value. So we're going to have to put the 2 in to the original equation to find out what the y value is. So I'm going to do that down here at the bottom. So it says negative, and I'm going to plug 2 in for each x in the original equation. And this will give us the y value of the vertex. So 3 times -3. So we end up with -3 times -3 is 9. So 2, 9 is our vertex. Now, on my graph, 2, 9 is not really listed, so I'm going to just go ahead and estimate where 2, 9 would be. So that's my vertex. And while I'm at it, I'm going to go ahead and draw my axis of symmetry, which is a dotted line. Remember, it's x equals 2. Then, might be a little bit harder on the iPad to draw in my quadratic, but there we have it. And I already labeled the x-axis of symmetry as x equals 2. Remember, it's always the x value of the vertex, and it's always written in the form of a line, x equals. For this next example, it says, suppose the path of the football is modeled by the equation y equals -0.025x times the quantity x minus 50. What is the maximum height of the football? So here we have a little picture here, and we have a person kicking the football. The maximum height up here would be at the vertex, the y value of the vertex, because y represents the height. The x value represents the time that it takes to get to that height. So we are actually looking for the y value of the vertex. Well, before we find the y value of the vertex, we have to find the x value of the vertex, which means we need to know the x-intercepts. This is in intercept form, which is why I'm searching for my x-intercepts first. So here we have x on the outside of that quantity as a factor, so one of our x-intercepts are 0, 0, and you can actually see that in the picture. And the other one is 50. That's your q value, 50, 0. So to find the x value of the vertex, you add the x-intercepts, 0 plus 50, and divide by 2, and you should get 25. So it's 25, comma, something. The y value, that's actually what we're looking for, is that maximum height, that y value. So then we substitute 25 in for both of the x's. Times 25, then 25 minus 50. So go ahead and take a minute and type that into your calculator. I'm going to pause it, also type it in my calculator, and get the answer, and hopefully you have the right one. Okay, here I went ahead and typed this calculation into my calculator, and I got 15.625. And remember, we are in, I think we are in feet here. I believe that's what it said. So 15.625 is the maximum height. Actually, it is in yards. So hopefully, if you did not get that, go ahead and double check. The next concept, the key concept, is the FOIL method. The FOIL method is used pretty exclusively from here on out in whatever math classes you're going to use. This is on page 14 if you wanted to double check in your textbook. FOIL method is really just useful with two binomials. So if you take a look at the example we have here, we have x plus 4, which is two terms, which is what we call a binomial, and x plus 7, which is also a binomial. So FOIL is really just a way to distribute. In the past, if you may remember doing generic rectangles to multiply, that's just a little bit more, not complex, but a little bit longer. It takes a little bit more than to actually FOIL. So that's what we're going to go ahead and multiply them. So the f represents the first terms. So in this case, it's in the red. So it's color-coded. The first terms are x times x, which is x squared. And then the outer terms are next. That's the O in the word FOIL. And they are blue in the color coding here. So the outer terms are x times 7. And when you multiply those, you get 7x. And then the I, which is green, stands for the inner terms, which are the ones on the inside, which is 4 and x. So when you multiply those, you get 4x. And then the L, which is looks like a purple color, which represents the last terms. You multiply 4 times 7, and that's 28. And then from here, we can combine our like terms. So on the inside here, we can add 7x plus 4x to get 11x. And then the other two terms of this trinomial are x squared and 28, and we cannot combine any more terms because they are not the same. Example number 5 says to write that polynomial, the equation, in standard form. So essentially we are just going to FOIL. So the first thing we want to do is, not that there's a single right way of doing this, I always multiply my binomials first, and then I'm going to distribute the negative after I FOIL. So keep my negative. And then when I multiply my first terms, that's your x times x, I'm going to get x squared. And then my outer terms in this case are x and negative 7. That's negative 7x. My inner terms are negative 2 times x. And then my last terms are negative 2 times negative 7, so that's positive 14. I'm going to combine my like terms. So I have negative 7x minus 2x. When I add those together, I get negative 9x. And then I still have the positive 14. And the last thing I see here is I have a negative that I need to distribute to my trinomial. So negative times x squared is negative x squared. Negative times negative 9x is positive 9x. And negative times a positive 14 is negative 14. So this polynomial is now in standard form. And this last problem, number 6, we have a polynomial equation in vertex form. So this one is a little bit more to do, so you want to make sure you have enough space. So the first thing I'm going to do is I notice I have a quantity that's being squared. So to make sure that you don't make a common mistake, when you square x plus 4 minus 10, so here it's x minus 4 quantity squared. You may not just square x and square 4 to get x squared plus 16. That is not proper. We do that if we have things that are multiplied together. So if that was 4 times x, then you would square each of them. But because they are not factors, they are add-ins, they're being added together or subtracted, you cannot go ahead and distribute that. So the first thing to kind of ward against that is to write out that binomial times itself, because that's what x minus 4 quantity squared looks like. So now, since I have it set up that way, I'm going to go ahead and FOIL those binomials. So x times x are my first terms. And then my outer terms are x times negative 4. And my inner terms are negative 4 times x. And then my last terms are negative 4 times negative 4, which is positive 16. And then don't forget to carry down the negative 10. Next up, order of operations says I need to do multiplication here. Actually, before I do that, I'm going to go ahead and combine those like terms in the center. So negative 4x and negative 4x is negative 8x. And then minus 10. And I'm going to distribute because multiplication comes before that subtraction. So 6x squared. 6 times negative 8x is negative 48x. And 6 times 16 is 96. And carry down the negative 10. And then I'm going to go ahead and combine my like terms. I have 96 minus 10 here at the end, which would add together to give me just a positive 86. So this is standard form.